Okay. I'll just summarize what we did with KNN in relation to the implementation. We saw KNN is a very simple algorithm that uses the entire data set in a training phase. Whenever a prediction is required, that is, whenever we have to predict for an unseen data, it searches through the entire training data set for K most similar instances, and the data with the most similar instance is finally returned as a prediction. So here searches may not be probably the right word. Searches seems that we are not doing a complete exhaustive search. So we are actually going through every data point and we're evaluating what is the distance between every training data point with every test data point or validation data point. And whatever is the closest, then K most similar, then we use that here. We choose K by using something called as a validation set. And with validation set, we will try different values of K, and whichever gives us the uh, highest accuracy is what we'll choose as the value of K. Okay. So the philosophy of K nearest neighbors is if you are similar to your neighbors, then you're one of them. Here we said these will be the steps we'll use. During the training phase, we'll store all the data. Sorry. And we'll calculate the distance between test and train data, or you can say test, validation, and train data, and find the K nearest points, predict the class based on majority, and check for accuracy. So here we started with iris dataset. We said we'll use NumPy, matplotlib for plotting. Some of the features of scikit-learn we'll use for model, especially for model evaluation. We take iris data by calling the load iris function. Once we have the data, we divide that into capital X and small y. Capital X is all the features. So there are 150 samples with 4 features. And small y is your 150 class labeled class. We see that y is in a sorted order. And the class is balanced. That is, all 3 classes have equal representation. We use train test split divide into 3 parts. So train test split only divides into 2 parts. So we do it in 2 sets. First time we divide it into 15 and 85%. We call the 85% as train, 15% as test. Then we take the 85% that is train data and further divide it into 20 and 80%. So 20% will be our validation data and the remaining becomes our train data. So that gives us 101 samples for train, 26 samples for validation, and 23 samples for test. Here we have used something called a stratify option. And what stratify option does is it ensures that uh, your target variable, that is y, is equally distributed between all the data points. I think I also need to run, otherwise let me execute these skills. Okay, stratify ensures that we have equal representation in all 3 cases. So when we do that, we see that uh, for train, this is the representation, for test, for validation, and then for test. We said training phase is just remembering the data. So let me go a bit faster now. We calculate the distance between train, validation, and test. We said we'll calculate the distance and we'll store it into a variable called as distance test, distance validation. Distance test is the distances between all test points and train points. So the size of that array is number of elements for test multiplied by number, like that will be the number of rows, and number of columns are dependent on number of training samples. Similarly, validation would be number of rows will be number of validation points, and train will be number of training points. Okay. So here we start with zeros. Uh, just to quickly put these values, the first 0 here represents the distance between the first test point and first train point, first test point and second train point, first train point and third train point, and so on. Okay, so this would, the entire row will be the distance of test point 1 with all the different test points, all the different train points. Second row would be all the test point 2 with all the different train points, and so on. Okay. So right now we are zeros. We'll have to evaluate the distance. We said, okay, we'll evaluate the distance using gradient distance formula. We take this formula, we test for a single sample what this looks like. So x test, so let me directly jump here. X test minus x test minus x train whole square, sum of that and square root of that gives us the distance. So we take that distance, we run it through a loop to evaluate the distance between all test points and all train points, and we end up with this matrix. We do the same for validation data, and then we have to find the value of k. So here we choose, let's say let k be 5. We sort it, we take all the distances, we get all the arguments, we get all the indexes of the distances, and we, okay, let me go ahead. And based on the indexes, we get the closest 5 points, and we say, let me take those 5 points and find out that for those 5 points, what are the labels? And we saw that these were the labels of those 5 points. We'll say, okay, let me take mode of this data. Taking mode of it gives us just one sample, which will be a prediction. And we said, okay, if we use this prediction, then uh, we can verify between our prediction and validation and see how good or bad we do. Okay. We said also let us check the accuracy. For accuracy, we use from scikit-learn the function accuracy score, and that gives us an accuracy of 88%. We had a discussion on confusion matrix as well, which gives us the actual values versus predicted values and how good or bad we did. And we talked upon two new terms of evaluation, precision and recall. Precision is whenever we say an answer, how often are we right? And recall is when we say an answer, how much is our coverage? How much have we covered? So I'll talk on this today a little more in detail. We saw that F1 score is a combination of precision and recall, and F beta score is again a combination of precision and recall, but it helps us put another factor called as beta, which gives us an option of choosing how much value do we give to precision, or how much value do we give to recall. Okay. Again, we'll look at this formula today in more detail to say how do we choose the value of beta. Okay. Uh, do a bit in validation for now. Okay. Then we said let us choose the right value of k. To choose the right value of k, we will do it on the validation set. We will try different samples of k. So here we took k going from 1 to 25. We are increasing with two steps, and running this, we say what is the let's look at the accuracies. So these were the accuracies. It's difficult to see here which one is doing good. See here, it is not very difficult. This one is the highest. But we said let us plot it out. So once we plotted it, we saw that okay, uh, sample three samples is giving us the highest accuracy, around 92.3%, and we use that for our prediction. K is equal to 3. Again, we do the sorting with respect to test data. So all of this we did earlier was with validation data. Now we do it with test data. We see the accuracy we get is 95%. And this is where we had stopped last time. Do you have any more questions before we continue?
Yeah, that F beta score and F score, what is the importance?
Yeah, I'll talk today. I'll
Okay.
talk about it. Okay. Any other questions? Okay. So let's go ahead. So if you see all of these steps, there are so many sub steps and so on. And if we have to actually use KNN for a different algorithm, it would be very difficult to use it in this format. Okay, finding distances and stuff like that. So what we do is we create a class out of it here, and creating a class is going one step towards object-oriented programming. Uh, and maybe a short description between, or if any one of you can answer, okay, can you answer what will be the difference between your procedural or linear programming with respect to object-oriented programming? Anand, you're saying something?
And no, I'm thinking something. Yeah.
Okay.
Hmm.
Okay. I'll volunteer. So linear, whenever we start learning programming, we generally start with linear or procedural programming. And within linear or procedural programming, the idea is you go from line 1 of code to line 10 of code. That is how many, whatever is your size, you go linearly, and you'll keep on doing whatever things are supposed to be done. You may have some nonlinearity in terms of if loops and functions, but for the most part, it goes from first line till the last line of code, and you run sequentially. Okay, so it's also called sequential programming or procedural programming. Object-oriented programming is having a different mindset towards writing code. So here the focus is we will talk about objects, and each object can have their own functions that will make sense in context of that object. And further, you may talk about some variables or data values or memory points with respect to those objects. Okay, so the focus is more on the object, and we write code for uh, we write code in terms of variables and methods that are relevant to that object. And so that feature of object-oriented programming is encapsulated or captured with something called as classes. Okay? And classes are very nonlinear in the sense you don't go from line 1 of code to line 10 of code. You talk in terms of objects, you create objects, so you're creating blueprints out of it. And whenever you initiate, whenever you take an instance of the class, that is when the object comes into existence, and then you can do all sorts of cool things with it. Okay? So here what we do is putting it into, and for me especially this was very difficult because all my life I've been doing procedural programming, uh, and I think most of us start that way, and unless you are working into an IT field or computer field, you don't really see the importance of object oriented programming. Only after coming to this project, only after dealing with data science for some time, I found that object oriented programming is really useful, especially in terms of what we want to do here. So if you see, we did a lot of steps here, right? And if you skip any of the steps, we will really mess up. Creating a class here will solve our problem. So here we're creating a class for KNN, and creating a class within Python is done by writing class, the name of the class, open close parentheses, and colon. If you're inheriting this from a different class, you will write the superclass, or what do you say, wherever you're inheriting from, the parent class inside. But here we are not inheriting anything. We are just starting with a new class, which has nothing to do with anything that has happened in the past. Within this class, we define several functions. There's a function called as init, train, predict, compute distances, and so on. Generally, if you want this class to store some values or data points or something like that, we will put that in the init function. The init function is is a base function. So for any class that you have, you need to have an init function. Uh, so Python, what you say, it forces you to write this function, okay? Even if it is empty, even if you're not doing anything with it. So this init function starts with two doubles and two underscores, init, and then followed by again two underscores. Okay? And whatever you give as inputs here will be passed inside, and you can store it into the self variable. So all class objects will communicate with each other using the self, what do you say, self object. So passing self to a function says that this function is being called by the object, which will be an instance of KNN. So maybe it's too complicated, but just remember to pass self, and then if you want to communicate between them, you can use self as a right. So in it, I don't call anything. Within train, as we said, for the training, the classifier is for KNN, it is just memorizing the data. So for train, we are passing two inputs, x and y. That is our features and our classes. When we pass x and y, we just store it into two variables. Self.xtrain will be our x, self.ytrain will be our y. Now, xtrain and ytrain thus become internal variables of this object. Okay. For the predict function, we say, okay, prediction is simple. We'll compute the distances, and we'll got two functions, compute distances. It will take x, which is validation data, or train data, it doesn't matter. We take x, which is validation or train data, and it will compute the distances. Okay. Once we have computed the distances, we will call something called as predict labels, and these predict labels will predict the distances between these k objects. Okay. So here we are assuming that we will the user will pass the k as well. Okay. How will compute distances work? Exactly as we saw earlier. Uh, we create a distance, what do you say, a distance matrix with the size num test num train, and we evaluate the distances. That is what compute distances will do. What predict table will do? It will do the other part. Once we have those distances, we will sort it and we'll find its mode. And returning the mode will then mean giving the prediction. Okay. So if I execute this class to use KNN, then I will just call the instance of that class. So I'll say KNN is my class and KNN classifier is the instance of that class. I will say KNN classifier dot train, pass it extend by train. So this is my training, and then prediction. KNN classifier dot predict x test with the number of k we have. So here we saw earlier that k3 works well. I put k3, I get the prediction. This is my prediction, this is my test. So all that we did earlier can be part of KNN. So it is very easy for us to use. What you can then do is, as we saw in earlier classes, we can create modules out of stuff. You can put this entire code into a Python file, and whenever you want to use KNN, you can import KNN. So we'll say from import from whatever file name you save, from file name import KNN, and you have KNN with you. You don't have to worry about the details of how you have implemented, and you can use it much simply. Uh, One more, since we are talking about classes and important things, we actually will not need to implement KNN like this because we can simply call KNN from scikit-learn. So from scikit-learn, I can do from sklearn dot neighbors import k neighbors classifier, and that's it. I've imported it from KNN from scikit-learn. Now, if I want to use this classifier, I can say k neighbors classifier. Let me create an instance of it in CLF. Go to CLF dot train, CLF dot fit. I'll give extreme, y train. Okay. Here I think I have to. I can also provide the number of neighbors. Okay. By default, neighbors 5 is chosen. I can say n neighbors is equal to 3. So this classifier will start with this. I have fit the data. Now, if to predict the data or unseen cases, I'll say clf.predict with x test. Let me store the answer in ypredict, ypred. And if I look at ypred and test. So it is as simple as doing this. You can simply import it from scikit-learn, and the task of training is very simple. Says predict clf.fit. Task of using it is very simple. clf.fit.
Elijah, in all these cases, we have to give this n members is equal to 3 or 5, whatever it is, right? There is no method where they will find that best k value.
There is. We'll be talking about it in detail, maybe after we finished our algorithms.
Okay.
So there is, maybe in short, if I have to answer you, there are two methods within scikit-learn, something called as grid search and random search, where so right now here KNN has very small number of parameters, only one parameter actually. You will, when you go to more advanced algorithms, you will see that you will have at least maybe around 7-8 parameters. Each parameter can have so many different values. So it will be very difficult for us to choose which one is the best case. So we create something called as a grid, and there is something called as grid search, which will be able to search in that entire grid, which is the best combination, and return to us. And there are automated functions for doing all of it. Okay. So we will talk about this when we, I think, finish our algorithms, and before going to another test case, we can talk about that and then go. Okay.
Right.
Yeah, do you have any questions at this point on classes or calling scikit-learn? Okay. Okay. So let me shift to my iPad screen. Sorry, I have not loaded my document. I have to update some things last night. Let me. So we discussed all of this. Let me go ahead. Okay. So we have done this part. We have gone to the notebook. We have seen how to implement KNN. We have put it into a class, and we have also checked from scikit-learn how can we import a simple classifier like KNN, and how can we use that. Okay. Going ahead, let's talk about evaluation. And I covered evaluation, some parts of evaluation earlier, but I thought I did not do justice to that part. So we'll talk a bit more about evaluation, and then we'll see how it works out. Okay. So here we're talking about two terms, something called as accuracy and precision. And you can see four examples of high accuracy with high precision. So accuracy is how close you are to the bullseye, how close you are to your answer. Okay. Precision is when you are giving, when you are putting out your answers, how close are your answers together. Okay, that is, you may be telling 10 things, you may be giving 10 predictions, but are all those predictions uh, close by? Okay, and that is what you mean by precision. Okay, so here is an example, the best case of high accuracy, high precision. That is, we are hitting 1, 2, 3, 4, 5, 6. We are hitting 6 times, and we are hitting 6 times at the bullseye. This would be an example of low accuracy and high precision. That is, when we are saying something, all of them are close, but accuracy is bad. That is, we are this much far from our bullseye. We are this much far from our actual prediction. This would be our third case, high accuracy, but low precision. So everything is around this bullseye, but we are not very close. Our answers are spread apart. That would be low precision. And this would be the worst case, low accuracy, low precision. So as good as random. Okay. So we are not even, not all of our points are not close to the bullseye. In fact, all of the points are very far spread out as well. So that is what, in layman terms, you would talk about accuracy and precision. We also saw earlier that accuracy is not a good measure always, okay, depending upon different cases. So here is when we talk about precision, and recall what are we talking about. Okay, so consider this to be your entire sample space, and within this sample space, we have data divided into multiple parts. Okay, so this entire region is false. Okay, let me say here. Uh, okay, so this entire area here is our relevant items. That is, let's say if this is our entire universe, and for this entire universe or this entire sample space of data, this is our values of 1. These are our true values of 1, and all of these are true values of zeros. Okay, that means we have to create a model, and the model should be able to predict the difference between this section and this section. Any data that comes from this section, our model should predict as 1. Any data that comes from this section, our model should predict as 0. Okay, so that is what this area represents. Now within this area, this is what we are predicting in our model. Okay, so anything, what our model is doing is anything inside this circle, our model is predicting as 1, and anything outside the circle, our model is predicting as zeros. Okay, so this is what has happened, right? Now, looking at this, if I ask you, what is our accuracy? What will your answer be? Which which sections will be on the numerator and which sections will be on the denominator for accuracy?
Circle will be our numerator and their square area will be our denominator.
He's saying circle is all the right points.
Yeah.
Accuracy is basically the number of right points divided by the total number of points.
Total number of points.
But all of this is not number of right points, right? Because these are wrong points actually. Circle is saying that everything inside is 1. But we know that these points are not 1. These are actually 2. Does that make sense?
Inside the circle, if we tell the whatever on the right side is 0, then that is also accurate, right?
Yeah, so let me define again what the circle means. The circle means that we are saying everything inside the circle is 1. Everything outside the circle is zeros. That is what our prediction is telling. Actually, everything here is 1. Everything here is zeros.
Okay.
Have you got the difference?
Not really.
So let me explain this again. Okay. So precision and recall are actually precision, recall, accuracy are actually a bit complex to understand the terms. So it takes time to drill in. So let me again explain. This is our universe of sample points. Left side of this line is all the true values, all the values that we need to predict as ones. Right side of this is all the values that we need to predict at zeros. Okay, so these are true values. Okay, true values of ones, true values of zeros. Now we have made a prediction called the circle. Everything inside the circle we are predicting as ones. Everything outside the circle we are predicting as zeros. Okay, have you got this now?
Yes.
Okay, now within that, when we talk about accuracy, accuracy is which ones we got right. Okay, compared to all the other ones. So which one we got right?
True
We got
positives.
these guys right,
Yes.
because we said that these guys, everything inside we said are ones, and out of this, these parts are actually ones. So we got this part right. We also got this part right. We said everything outside the circle are zeros, and these part are actually zeros, right? So our accuracy would mean this one plus this one divided by all of these points. Does that make sense?
Yes.
Okay. So accuracy would be true positives plus true negatives divided by true positives plus true negatives plus false positives plus false negatives. But yeah, my interest is not in accuracy right now. My interest is in precision. Let's say precision and recall. So precision means how many items, how many selected items are relevant. Okay, how many selected items are relevant. So these were our selected items. Okay, and within this selected items, these much are relevant items. That means these ones we wanted to save as 1. Okay, so our model was trying to predict how many ones are there. We predicted that this entire thing are ones, out of which these ones are truly ones. So we say, what is a precision? A precision is this divided by all that we said 1. We said that all of these guys are ones, out of which we are only right these many number of times. So a precision becomes how many times you are right divided by the total that we are saying as ones. Does that make sense?
Yes. Yes. Yes.
Okay. Now, in contrast to that, we are saying how many relevant items are selected. Okay. So here we are talking about a different thing. We are talking about coverage. Okay. How much have we covered? So Here we said all of these guys are ones, of which we know that we have got these ones rightly. So we have got this ones rightly as our what do you say, as our predictions. These ones are right, but how many have we missed? We have missed all the other points here. Okay, so in that sense, we'll say what percentage of area have we covered? So we'll say okay, we have covered this much out of this much. That would be our recall. Okay, so if you remember our Excel that we had made that day, we talked about, I think our answers were something like this. Okay, let me not confuse you here. Okay, if you have understood this concept, then we will go to the next point, and then yeah, no, I have not put a slide for confusion matrix, but we will look at confusion matrix. That will make more sense. Okay, but in essence, have you got what I'm trying to say regarding precision and recall? If I have to again rephrase it, I'll rephrase it. Okay, precision is you're giving some outputs, you're giving some predictions. How often is your prediction correct? Okay, that is what we mean by precision. Your recall would be you're giving some output. How much are you correct? Okay, how much are you correct in the sense of have you left out something else or not? And that is your idea of recall. Okay, so can you can you give me an example where we can get 100% recall and I don't really care about precision. Okay? If I have to get 100% recall, what kind of model I could prepare?
Yes, just input equal to output. Whatever everything is, just say true.
But yeah, not input equal to output. Irrespective of the input, we say true.
True, yeah.
So if we said everything is true, you will get 100% recall because out of all these points, you have captured everything. That will be your recall. But you will be wrong so many numbers. Your precision will be low. Why your precision will be low? Because all that you say is true. Not all of them are true. Only these guys are true. These ones are wrong. These ones are not true. Okay. So you'll have 100% recall, but you'll have bad precision. If you want to have very good precision, what you will do is you will give just one output. Let's say if you just take this output and you say that this is true, okay, and you say everything else is wrong, but this is true, you'll have 100% precision. Why? Because you gave one example as true positive, one example as positive, and it actually is positive. So you will have 100% precision, but you will have very bad recall because you have missed all the other points. An ideal model would be like this. Our ideal model would be this rectangle. Our ideal model would be this rectangle, which will say that everything inside this rectangle is ones, everything outside this rectangle is zeros. Okay, so you'll have 100% precision, you'll have 100% recall. Okay, so even if you don't understand the whole thing, if you just remember the concept of precision and recall. Precision is when you are saying something is right, how often are you right? Okay, and recall is when you're saying something right, how much have you covered? Okay, or this is also very good play on words. How many selected items are relevant? That is your precision. And how many relevant items are selected? That is your recall. Okay, so you can think of any terminology that helps you to understand this concept and then use it well. Okay, if you're going for interviews, people will generally ask this question for data science: what is precision, what is recall? Because many people would just try to wrote the formula. The formula for precision then would be something like this: true positives, this way. Formula for precision will be true positives divided by true positives plus false positives. And formula for recall will be true positives divided by true positives plus false negatives. Okay. So many of the times people will just remember the formula and they say that would be enough. But I believe if you understand the concept, then you can come up with the formula anytime. Getting the formula is not very important. Okay. Let me go ahead. Now, generally, when you have multiple metrics, okay, when you have precision and recall, it will be difficult for us to choose which one is better. So let's say I give you two models. Uh, One model is having a precision of 80% and a recall of 80%. One model has a precision of 90% and a recall of 75%. Okay. So if you have to say which one is better, it is very difficult for us to find which one is better. Okay. Uh, so what we do is we say that, okay, instead of two numbers, I am interested in one number that will give me an overall picture of what is good and what is bad. Okay. So to get that one number, we have something called as F1 score. And F1 score says that I will give equal importance to precision and equal importance to recall. It is evaluated using this formula, which if you observe closely, this formula is basically the harmonic mean of precision and recall. So if you do 1 divided by 1 by precision plus 1 by recall, you will get this formula. Okay? So taking the harmonic mean of precision and recall gives you F1 score, which gives equal importance to both these guys. Okay. So sometimes this is a very good metric. Instead of using precision and recall, you may get confused. F1 score will give us a combined answer of everything. That is very useful. Okay. So we can use F1 score as our decision maker in choosing which model is better. Further, you may sometimes want, depending upon which problem you're trying to tackle, you may want a different order. Like you may want different priority for precision, different priority for recall. Okay, so sometimes you may want more precision, or sometimes you may want more recall. Okay, so let me uh, take an example. Uh, okay, so let's say you're trying to uh, Okay. Okay. So let's consider this case where you have a traffic signal, and on that traffic signal, you have an automated system which will scan uh, if scan if someone is breaking the signal or not, and when someone is breaking the signal, you have your picture of the number plate, and your code automatically extracts those numbers, and then you have which vehicle has broken the signal. Okay. Now, in this case, precision would mean when you give the answer that this number plate has actually broken, you are right. So 100% precision would mean every time you give an answer, you are extremely sure that this is the person who has broken the signal. This is the vehicle who has broken the signal. Okay. And recall would mean that everyone who breaks the signal, you catch every one of them. Okay. So let's say 100 people are breaking the signal. Precision would mean, so within right precision, you would say, let's say 70 people, you can be extremely sure, 100% right, that these 70 people have broken the signal. And recall would mean you would take 100 examples or more examples and you will catch all of these guys. So even if you give 150 predictions, out of those 150 predictions, your 100 examples are already included. Okay, 50 you may be of this 50 extra that you have said may not be the right ones. Okay, or maybe it can happen that 150 examples you say are broken the signal. Out of those 150, 80 belong to this group, and 70 people are not actually breaking the signal, and you're still saying that they have broken the signal. So in this case, what is more important? Is precision more important or recall more important? Okay, can you make a guess?
Precision is more important.
Yeah, precision is more important, right? So when the traffic signal is actually charging someone, you should be 100% sure that they have actually broken the signal. If you have many such examples of this, that you're charging people who have not broken the signal, then your model is not right. Okay. So in this case, we see that even though the task is of prediction, we are more we are more interested. Okay. So in this case, we think that okay, precision is again more important, right? So here we have something called as F beta score, which has an additional term called as beta. Okay, and this beta is multiplied here in the bottom for precision, and we have a beta here, beta square here. Okay, so can you tell me, looking at this one and this one, what value of beta will give you exactly as F1 score?
1.
Okay, excellent. Then beta is 1, you will get up this formula for F1 score. And when beta is 0, what will you get?
Record.
Yes. So when beta is 0, so lower values of beta, beta closer to 0 will give more importance to recall. Okay. Beta greater than 1 will give more importance to precision. So depending on what we want. So if we want more importance on precision, I can give beta as maybe 5, 10, 15, depending on how much importance I want. And that will give more importance to precision. If I'm more interested in recall, so an example of recall would be you have cancer patients and you are testing their, you have access to their MRIs, and from that MRI, your model has to predict if someone has cancer or not. Okay. So your model will predict, then you will verify further, and then based on that, you will say to the patient that we'll start the relevant treatment for the patient. So in this case, uh, even if we identify few examples as wrongly having cancer, that is not a problem because the model will give something, and then you have the human doctor who will verify. But your model should not miss out any examples. Okay, if your model misses out any examples, the human will not even out of thousands of different MRIs that you scan, the human may not even know to verify, to check something or not. Okay. So in this case, we will give more importance to recall. So you will take your beta to a lesser value and so on. So again, this depends upon a case-to-case basis, which is more important or not, depending upon our case. Especially for anomaly detection examples, we want more of recall uh, rather than precision. Okay, so maybe Anand, if you remember, we were working on
Yeah.
the helicopter problem, and we were more interested in recall. That is why within the problem statement, they had said that they will be using F beta as their evaluation metric, and beta had a certain value. Beta, I think, was 0.4. It said that recall will thus be more important than precision. Okay, so going ahead, we talked about this, but I wanted to stress a little bit more upon this. When you get your example, when you get your data set, so let me say this is my entire data set. One way of training my model or evaluating my model is I will take that data and divide it into three parts. Okay, training set, validation set, and test set. Okay, so of all the data, I will train my model only with this part of the data, which will be used to fit the model. Fit the model as in help the model to learn the parameters. KNN is a very bad example because we don't do any training. But just remember this idea of division. And when we go to more advanced models like naive-based decision trees, you will see how this fits in. Okay. So for training purposes, there is something called as different parameters for this model. To fit this model will have certain parameters. Okay. And to choose which parameters work best, we use the validation set. Okay. What does that mean? I will fit the model using the training data. I will test it on validation set. Validation set, my model has not seen yet. I will do the same model. Let me draw here. So this training data will go to my model, and this model will get fit. Then I will use this validation set to this model. The model will give out some predictions. These predictions I'll verify with validation answers that I have. So let's say evaluation. And based on this evaluation, I will use that as feedback to train the model. Okay. So this evaluation will be used as feedback to further choose which parameters are right or not. Okay. So training set is used to fit the model. That is, it is used to uh, yeah. So maybe it is more advantageous to talk in two types of parameters. We can talk about for the model what parameters it has. Let's call it something called as parameters. And here for validation, let's call it hyperparameters. Hyperparameters are decided one level above the parameters. So let's say here, let's say we have a training model which requires you to train theta 1, theta 2, theta 3, and so on. Hyperparameter would be something like how many thetas do I have? Do I have 5 thetas? Do I have 7 thetas, and so on? And that would be the kind of decision you're making with validation set. And training these parameters, what should be the value of theta 1? What should be a value of theta 2? What should be a value of theta 3? That would be using the model data here. Uh, this would again be complicated to understand for now, but just remember my words, and when we go deeper into uh, model fitting and parameter selection, we'll understand what this means. So a training set used to train the model, validation set used to decide the parameters for this model. Once we have something with good validation accuracy, we say that, okay, now we have a good model. Then we'll use that for test set. We'll use the test set to evaluate that model, and we'll get a final number. And you will use that number as a benchmark or as a criteria for choosing which model do we go ahead with. Now, the advantages of this method, it is fast and it is simple. The idea is very simple. You use this for model training, you use this for parameter selection, you use this for evaluation. The bad part or the con is we are using bad use of data first. Bad use of data means my model is only seeing this much part of the training. I'm using a very small, so this much part of the model, this much data I'm not training the model with. Okay, so we can use this simple method when you have lots of data. If I have lots of data, then we can go ahead with this method. It is called threefold split. Threefold split. Going ahead, we have something called as cross validation, where the idea is that we will take all of our uh, training and validation data. So if I take this entire part I will use for training the model. So I get more of the data to train the model. But what I'll do is I will split my data into multiple parts. So if this is my training plus validation data, I have divided into 5 folds. Okay, I've divided into 5 folds: fold 1, fold 2, fold 3, fold 4, fold 5. In the first example, what I'll do is I will use fold 1 as validation, and I will use all the other folds, fold 2 to fold 5, for training. So I will train the model with this case, that is, train the model with this much, evaluate it on this much, and get some validation accuracy, let's say 88%. In the second run, so these are multiple iterations, that will be the first iteration. In the second iteration, I will use the second fold as validation and everything else as training data, and I will get some other accuracy, let's say 87%. Why these accuracies may differ? Because I have different validation sets, I have different cases on which I'm testing the model. Third iteration, I will use this for validation, use everything else for training, and similarly you get the idea. Okay, and late in the last, I have these multiple validation accuracies. I will take the mean of those accuracies, and I will say that this, whatever accuracy I get, so let's say I end up with something like 88%, I will say 88% is my cross validation score. So cross validation is I am doing validation with respect to uh, everything else of my data. Okay, and my validation set actually covers the entire training set. So all of my data is getting evaluated, uh, and at the same time, uh, I get more data to train the model with. After I have done my cross validation, what I'll do is I will take, so using cross validation, the idea of cross validation is we will do hyper parameter selection. After we have done hyper parameter selection, we are sure of what parameters we are using. Okay, then we take all of this data and then train the model with it. All of this data means This is one data. All the others are just copies of it. Okay. Here, the advantage is this is more stable. Why more stable? Because in the first case, you're just testing with one validation. You're not sure if if you have other parts of the data, how your model will do. So in this case, we are more stable because we have used each sample of our data as validation, and we're testing it against other things. You get more data because now you get this extra part of data to train also, so you can see how good or bad your model is doing. The con is it is slower. You have to run 5 iterations of this. In this case, you just run one iteration and you're done. Here you have to run 5 different iterations for each example. So it becomes lots of training to be done. And if you don't have a good method of automated method of doing it, it will be very difficult. But luckily, we've got very good functions available with scikit-learn and other things where we can do cross validation very simply. Have you understood this part? Okay. Uh, let's continue maybe next time, uh, and we will take it from here the other part. Okay. Stop.